Batteries power modern life, from smartphones and laptops to electric vehicles, medical devices, and industrial machines. Batteries store and deliver energy whenever it is needed. They allow technology to function independently of constant power sources, making modern systems portable, flexible, and reliable. Despite their small size, batteries are complex devices built through carefully controlled industrial processes. Inside each battery, chemical energy is converted into electrical energy through precise material interactions. This transformation must happen safely, consistently, and efficiently over thousands of charge cycles. Modern battery manufacturing combines material science, automation, and strict quality control. Every step is designed to ensure performance, reliability, and safety at large scale. In this video, we take a closer look at how batteries are made, from raw materials to finished energy storage units used around the world. Battery production begins with carefully selected raw materials. Depending on the type of battery being produced, these materials may include lithium, nickel, cobalt, manganese, graphite, zinc, or other specialized compounds. Each material serves a specific function within the battery, contributing to energy storage, stability, and performance. Purity is extremely important at this stage. Even small amounts of contamination can reduce battery capacity, shorten lifespan, or create safety risks. For this reason, raw materials are refined and processed under strict industrial standards before they ever enter the production line. Once refined, these materials are transformed into fine powders or thin sheets. Their particle size, consistency, and chemical composition are carefully controlled. Automated systems measure and mix precise quantities to ensure uniformity across large production batches. Different battery designs require different material formulations. Some batteries are optimized for high energy density, while others focus on durability, fast charging, or long cycle life. These decisions are made long before assembly begins, as the choice of raw materials directly determines how the battery will perform in real-world applications. By the end of this stage, the foundational materials are fully prepared, setting the stage for electrode production and cell assembly. After the raw materials have been prepared, battery production moves into one of the most critical stages: electrode manufacturing. The electrodes are the core components responsible for storing and releasing energy, and their quality directly affects battery performance, lifespan, and safety. To create the electrodes, refined active materials are mixed with binding agents and conductive additives. This mixture forms a thick, uniform slurry that must maintain precise consistency. If the mixture is too thin or too dense, it can lead to uneven coating and reduced efficiency. The slurry is then applied onto thin metal foils using high-precision coating machines. Typically, copper foil is used for the negative electrode, while aluminum foil is used for the positive electrode. These foils act as current collectors, allowing electricity to flow efficiently through the battery. As the coated foils move through the production line, they pass through large drying chambers. Here, controlled heat removes solvents from the slurry, leaving behind a solid, stable electrode layer. Temperature, airflow, and timing are carefully regulated to prevent defects such as cracking or uneven thickness. Once dried, the electrode sheets are compressed through a process known as calendering. Heavy rollers press the material to achieve the correct thickness and density. This step improves contact between particles, enhances conductivity, and ensures consistent performance across the entire surface. After compression, the electrode sheets are inspected using automated systems. Cameras and sensors check for defects, thickness variations, and surface irregularities. Any sections that fail to meet strict specifications are removed before assembly continues. With the electrodes completed, the manufacturing process shifts to cell assembly. This stage brings together the positive electrode, negative electrode, and separator material. The separator is a thin, porous layer that prevents direct contact between the electrodes while allowing ions to move freely. Depending on the battery design, these components are either stacked in layers or rolled into a tight cylindrical shape. Cylindrical cells are commonly used in consumer electronics and electric vehicles, while flat or prismatic cells are often used in larger battery packs. Assembly takes place in highly controlled environments. Humidity and dust levels are carefully regulated, as moisture or contamination can damage sensitive materials. Automation plays a major role here, with robotic systems aligning and assembling components at high speed and extreme precision. As the cells are formed, they are inserted into protective casings. These casings provide mechanical strength and help shield the internal components from external damage. Each casing is designed to meet specific safety and performance requirements. Throughout assembly, continuous monitoring ensures that alignment, pressure, and positioning remain within strict limits. Even small misalignments can lead to internal resistance, reduced capacity, or potential failure during operation. By the end of this combined stage, the battery has taken its recognizable form. What began as raw materials has now become a structured energy storage cell, ready for electrolyte filling, sealing, and final testing. Once the battery cells are fully assembled, the manufacturing process moves to electrolyte filling. The electrolyte is a critical component that enables the movement of ions between the electrodes, allowing the battery to store and release energy. This step is performed under tightly controlled conditions. Because the electrolyte is highly sensitive to contamination, filling takes place in dry, clean environments where humidity levels are carefully regulated. Even small amounts of moisture can negatively affect battery performance, reduce lifespan, or create safety risks. During filling, a precise amount of electrolyte is injected into each cell. Automated dosing systems ensure that the correct volume is added every time, maintaining consistency across large production batches. After filling, the electrolyte is given time to fully penetrate the internal layers of the electrodes and separate a material. Once the electrolyte has been absorbed, the battery cells are sealed. Sealing protects the internal components from air, moisture, and external damage. This step is essential for maintaining chemical stability throughout the battery's operational life. The sealing process must be both strong and precise. Advanced inspection systems immediately check seal integrity to detect leaks or imperfections. Cells that do not meet strict standards are removed before testing. At the end of this stage, the battery cells are fully enclosed, chemically active, and ready for the final formation and testing process. Before batteries can be shipped or used, they must go through a critical activation phase known as formation. During this stage, the battery cells are charged and discharged for the first time under carefully controlled conditions. This process activates the internal chemistry of the battery. As the cells cycle, a stable internal structure forms on the electrodes, which is essential for long-term performance and safety. Formation is a slow and energy-intensive step, but it plays a key role in determining battery lifespan, capacity retention, and overall reliability. Throughout formation, each battery is continuously monitored. Engineers measure voltage, capacity, internal resistance, and temperature in real time. Any cells that show abnormal behavior, such as overheating or irregular voltage changes, are immediately removed from the production line. After formation, the batteries undergo additional testing. These tests verify that each cell meets strict specifications for performance, efficiency, and safety. Stress tests may also be conducted to simulate real-world operating conditions, including repeated charging cycles and varying loads. Only batteries that pass all testing stages are approved for final use. Cells that fail are safely recycled, allowing valuable materials to be recovered and reused in future production. This final evaluation ensures that only stable and reliable batteries move forward into packaging and application. Battery manufacturing brings together material science, precision engineering, and strict quality control. From raw materials to finished cells, every step is designed to ensure safety, reliability, and consistent performance at large scale. What appears to be a small and simple object is the result of a highly controlled industrial process. Each battery must store energy efficiently, operate safely, and perform reliably over thousands of charge cycles. As technology continues to evolve, batteries remain a critical component of modern life. They power everyday devices, support electric transportation, and play an increasingly important role in global energy systems. Behind every battery is a complex manufacturing process, quietly enabling the systems and technologies that shape the modern world.